All right, everyone. So let's talk about database indexing today. It's like one of the most important parts to know about when learning about databases. So in this video, we're not going to, really go into nitty-gritties of it. We're just gonna get a introduction and sort of overview of what the thing is, how it works, and all that. I'll give you some pointers where to go to check out the data structures we're going to talk about in detail, and all the types of indexing and all that things. So um so in a database, let's say we have a table like this, like a student table with the ID, the name, and the marks, and we want to run some queries like this, the query 1 and query 2. We want to get the name of the student whose ID is 1, or we want to get the name of the student whose marks is more than, let's say, 45. All the students. Now now the thing is, what can we do? Let's say we have a table of, let's say, millions of rows, let's say a billion rows, so what can we do? We can, just go ahead and check all of them. Let's say I want the student whose ID is 1. We can just go and check ahead with all the rows and, get the required one, right? But that would be quite slow. There are millions of rows, you cannot scan every one of it, so that's not really a feasible solution. So what do we need to do here? So herein the concept of an index comes into play. So indexes are basically columns with which you can search the database very fast, or you can get a row or like a group of rows very fast, right? So in this case, let's say ID is our index, right? Let's say this is our primary index, or a primary key. Let's say marks can also be an index for like the second query, which we will come to later, right? So let's say for now, the only index we have is the ID. So the ID can be an index, the marks can be an index, the name even also can be an index. So index is like a column with which we want to search the database, and we need to decide what indexes we want to use in a table when designing the database, because when designing we need to think about what kind of queries we are going to execute on this database, and accordingly we decide how our tables should look, right? Now we need to understand how this index helps us. Like, how can we do a fast search on a table of a billion rows? Now, when we talk about search, let's say I want, get me information of this object, get me this object whose ID is 1. When we think about that, we need a data structure like this. What comes into our mind? So you can think about that, right? What comes into our mind? How can we actually have a data structure, an auxiliary data structure, that can actually help us to get to a row whose ID is given to us very quickly? Now you might think about something called a hash map, and I hope you know what a hash map is, and I'll encourage you to take a look if you don't know what it is. So what a hash map does is, you can have the IDs and you can map it to the, let's say, the row, right? And you can search with any ID in a hash map, and more or less every time you will get it in in a constant time, and then you can just show the row. So in a in a database, we have two kinds of files, right? So we have the data files, where the actual data is stored, and how the data is stored in pages. For that, I'll suggest you to take a look at my video about slotted pages. That will help you guys. And we also have the index files. So let's say we have a hash map index. We will store the hash map in one way or the other in the index files. And again, the index is also stored in terms of pages. Everything in a database is stored in terms of pages, and how exactly that page is organized, you can take a look at the slotted pages video. So the index file may, let's say, contain a hash map of id, right? And let's say for id1 it will have a pointer to somewhere in the data file, right? For id2 it will have a pointer to somewhere in the data file, right? Now when we say, okay, I need id1, you can just go ahead, you have the pointer already, you can just read that part from the data file and you will get the row you want. So this, guys, is called hash indexes, and this does exist in actual databases. This is very fast when you just need to do this operation where id equals to 1 or where marks equals to 42, something like this, only equals to. Because as you can understand that hash map cannot fulfill our needs when we have queries like this, marks greater than 45. We cannot have range queries. We cannot have queries which selects multiple of those, because then we have to do a sequential scan or we have to keep our hash map sorted and all these things, right? So hash map, as you can see, is not really helping us in all cases. So we keep on our journey to finding our next data structure. So guys, let's say when you have to do a search on a space and you are given a range that the numbers you need to find is greater than x and it's smaller than y, or the numbers you need to find is greater than x, what kind of data structure that we should go for? Now if you remember your data structure classes, one search data structure, a very important data structure, is a BST or a binary search tree. Now if we use a balanced BST, I think this is called AVL tree, I'm not sure. If we have a balanced BST, then every time we will get O log n of search or O log n inserts. Now notice this is not as good as the hash map when we're searching, because hash map we will most probably get our data in O1 in constant time. But as you saw, that hash map doesn't actually fulfill all our requests. So that's why we need a tree kind of data structure, right? Because only tree kind of data structures help us to get us a bunch of numbers, a range of numbers, a group of numbers, something like that, right? So what's a BST? Let me give you a refresher. So, right. So the BST is, let's say we have something like this X, all these nodes in this subtree, in the left subtree, must have values less than X, and everything on the right subtree must have the value greater than X, and you might take somewhere less than equal to X or greater than equal to X, right? So this is our fundamental structure in a BST. So you can see that when something is, let's say my query that I showed you was marks less than 45, right? So if we have a BST created, a binary search tree created from that data, right, from that marks data, and all the nodes in the BST had a pointer to the actual data file, right? So we can get to some node where it's, let's say this node has got the value of 45, right? So we know that all the nodes under this subtree, sorry, not the full one, we know that all the nodes under its left subtree is less than 45. So we can easily get a bunch of we can easily get a subtree which actually represents all the data we need. So we can follow, and all these nodes, as I told you, has a pointer to the data file, and we can go to the data file and just pick up only the rows we need. So we can do it relatively fast, right? Now we are at a point where practical considerations come into play. Now what is a database primarily used for? It's used to insert and retrieve data relatively fast from a secondary storage, from persistent storage, right? Now, in a persistent storage, it's not like the RAM where we can move around nodes a lot, we can change the structure a lot. So what happens in a balanced BST, right? The balanced word is important. Now, in a balanced BST or in any balanced tree, the height of two subtrees, right, cannot differ more than one. So the height of the left subtree from a node and height of the right subtree from a node cannot differ more than one. So what we have to do is, as numbers keep coming in, as elements keep coming in, we need to rebalance the nodes. We need to take some node from here, and I'm not going to detail how the algorithm exactly works. You can take a look about that. We can take a node from here and shift it somewhere here, or we can replace this with the root, and we can do a lot of rebalancing, right? The problem is in a database scenario, the indexes are so large. The index, let's say the index might be of 3 gigabytes. The index file is of 3 gigabytes. You cannot pull in the whole index in your RAM and operate on it. You need to pick up some parts of it in the RAM, and then you need to go back to the secondary storage and write it. So the more rebalances we need to do, the more read and writes we need to do with the secondary storage, and that's something we do not want to do, right? Because secondary storage reading and writing would be slower, and that's what we need to control. So at this point, we need to come up with a modification of this data structure. We need to come up with a new data structure which solves all these problems, that we don't need to rebalance it quite often. So that's why people who are much more intelligent than me or you came up with something called a B tree. Now, what a B tree is? What is a B tree? B tree is something like let's try to understand it from a perspective of a binary search tree, right? So B tree can have a group of how can I say, a group of numbers or a group of elements in a single node, right? So let's say we have 1, 2, 3, right? Let's say the branching of this binary search tree is, of this B tree is 4. Now I'll come to what branching is or whatever. So let's say we can have a branch like this, and this subtree will contain everything, all the numbers, all the elements that is greater than 1 and lesser than 2, right? We can have something like this. This will contain everything that is greater than 2 and lesser than 3. And we can have something like this, which will contain everything which is just greater than 3. We can actually also have something like this. Now this subtree will contain everything that is lesser than 1, right? So this actually has as I told you, the branching factor of 4. That means there are 4 pathways going out from a single node. Like you saw in the binary search tree, we're going with 2 pathways from a single node. In a B tree, we are going with multiple ones, and rest of the things are similar. Now I won't also go into the details of how the operations are done in B tree, like how to do an insert or how to do an search. And a search is a simple thing, right? You understand how to do. If something, let's say we have a number, let's say 5, we see, okay, it's greater than 3, so we go to this subtree, and let's say this has got 6, 7, 8, and we know that we need to go to this subtree to find our 5, right? So B tree is also a balanced data structure. That means the subtrees won't have a high difference of more than 1, and that's how we can query a B tree. We can get a bunch of nodes very fast. And B tree is because it has a larger number of nodes per level, we don't need to do a lot of node rebalancing. So we don't need to take this node and move it somewhere else. We can make changes in nodes and create new nodes. So I won't go into detail of how exactly those operations are done. So the B tree is the like the quintessential index data structure that we have in our databases. Actually, there is another data structure called B plus tree, which is almost as similar to the B tree. The only difference is in a B plus tree, the last row or the leaf nodes, the last level or the leaf nodes must have all the elements of that present in that tree. That actually makes it easier after a point to get all the data. Now there are many variations of this B tree which are used to make it more optimized and make maybe some B trees for some special cases and all, right? But all of the data structures more like revolves around the basic structure of a B tree, and that's how actually we get that's how we can actually use a tree kind of data structure to actually have fast database reads, right? So the data structure class that you took, it doesn't seem, very useless now, right? Does it? Because databases kind of are the backbone of most software, and without having trees, we wouldn't just be able to make any use of it. Yeah. So to give you a bit of summary, indexes are like auxiliary data structures. Auxiliary data structure which stores any column of our table in a special way, so that we can access some rows of that table on a given query very fast. And as we found out, that a data structure called B tree and data structures associated with that are very useful to us in doing some of these tasks, right? So these are the basics of indexing. Now you might think that, okay, let's make indexes out of all the columns, right? That would be very useful. We can query on any column we want. That would be good. But wait a minute, guys. Look, in software engineering and in life, most things are not free. So indexing is also not free. When we do indexing, we are losing on few things, right? When we create more and more indexes, we are losing on our storage space. So the more indexes we have, the more storage space we will consume, our database will consume. And sometimes the indexes grow so big, it grows so big in size that it's actually unmanageable. And for that reason, I think Uber moved from Postgres to, I think, MySQL, because in Postgres the indexes were just getting too big after a point of time, right? So it's not free. The next problem indexes introduce is it diminishes our write performance slowly. Because see, let's say there is no index on this table and I want to write something to this table. I want to add a new row. Now what we do is we will just go there and add our new row, right? If there is no index, right? But if we have an index, let's say we have an index on ID, or we have an index on marks, let's say we have a B tree index on a marks, we need to also insert this 100, this marks and the pointer to this row to that B tree. To insert that B tree, we need to do some more secondary storage rights. We need to read from the index. We need to run an algorithm which is probably O log n, and insert this data into not only into a table but into an index too. So the more indexes you make, the write performance becomes slower, and if the lesser indexes you have, the write performance is better, but you cannot query on more rows, right? So because if you are querying on if you are putting a row which is not indexed in your where clause, then your query would be like super slow, right? It would just not even make sense how slow it would be. So that's kind of the overview of using database indexes. Again, if you want to know how exactly all these things are stored in pages, you can take a look at my slotted pages video. I'll probably maybe make another video on how exactly we are mapping these B trees, B plus trees data structure into a slotted page structure, and maybe even on the details of the B trees and the B plus trees. If you want those, do leave a comment and obviously like the video, subscribe to the channel, increase the traction of this video. I mean, well, as you can see, my channel is like a small one, and well, whatever, right? So help me make this channel bigger. So okay, so if you have any questions, put it down in the comments, and if you think anything was bad, anything was not, I was not right in some aspects, which I'm wrong often, you can also put those down in the comments. All right, till then, see you on the next one.